Ladies and gentlemen, this RedGamingTech.com video, we're going to continue our analysis of the Xbox One's developer interviews. Previously, we'd spoken about the CPU, we'd talked about why they'd made certain decisions, and a lot on virtualization. Now we're going to continue, and we're going to start things off with the ESRAM and the memory configurations and so on. So Nick Baker begins, and he said, I think in terms of getting the best combination of performance, memory size, power, GDDR5 takes you into a bit of an uncomfortable place. Having ESRAM costs very little power and has the opportunity to give you very high bandwidth. You can reduce the bandwidth on external memory. That saves you a lot of power consumption as well, and the commodity memory is cheaper as well, so you can afford more. That's really the driving force behind that. If you want a high memory capability, relatively low power and a lot of bandwidth, there's not too many ways to solve that. Now, we've already addressed this question previously, but I'm going to go into it again. This question was actually raised a couple of weeks back, but still. Obviously, as we're going along, I'm giving my thoughts on this and Microsoft's answers. Okay, I'm going to start out by saying that the reason that they went with DDR3 is because they didn't think they would be able to get 8 gigs of GDDR5, right? And also they wanted to reduce the cost of production. Now, when they are talking about commodity memory, they are talking about DDR3. So there's 2 points I'd like to address. I don't like where he's saying it takes you in an uncomfortable place, because I don't see how it does. There's no uncomfortable place with GDDR5. It's not, this, and I think Sony are kind of guilty of this as well. They're putting a lot of mysticism into GDDR5. They're saying it's like, I don't know, some kind of savior, and it's not. It's just, a different memory technology, and it's not really anything to say about it. It just gives you a lot of memory bandwidth very easily. Obviously they have 176 gigabytes per second. Microsoft have 68 with the DDR3 and 200 odd with the ESRAM. Now, when they're talking about this uncomfortable place, GDDR5 memory actually requires lower voltages than DDR3. That's well known. You can Google it yourselves if you really wish to do so. When they're also discussing, well, you can have more of it, I've already heard people tear them apart for that response, actually, because people have said, well, why didn't you put 16 gigs in then? Yeah, why didn't you just, load the sucker up and then be done with it? Why are you talking about cheap commodity memory, but then just put in 8 gigs? I think there's a couple of reasons behind that. One, they're trying to reduce costs because DDR3 memory is still quite expensive when you're putting a lot of it in. Two, I think that they don't really expect in this generation to go over the needs of 8 gigs or whatever they're allocating towards games like 5 or 6 gigs. They think that at the moment that amount of memory is going to be more than sufficient for the foreseeable future. There's a lot more I want to say on this, but I'm going to leave it for now because there's still a lot more questions we have to go through. So, one of the points as well is that Intel, of course, were using EDRAM. That was with Haswell. Meanwhile, Microsoft decided to go with ESRAM, and the reason behind this, according to Nick Baker, is because it's just a matter of who has the technology available to EDRAM on a single die. And so they didn't actually end up wanting to go with a daughter die. They actually wanted to go with a single processor. And they said, and I quote, if there had been a different time frame or technology options, we could have maybe gone with a different technology there, but for the product in the time frame, ESRAM was the best choice possible. So what he's basically saying is that for their budget, for the time that the system was released, for the time that they were developing it from, ESRAM beat the EDRAM. As well as I'm probably guessing the fact that it was easier for AMD to implement and much more besides. So one of the things that we've discussed quite heavily, and this comes to us from the Hot Chips presentation way back when, If you want more information on that, you can simply search hot chips on the channel. But they actually Microsoft unveiled that there were 4 blocks of 8 megabytes. So obviously, it looks like there's basically 32 megabytes split into 4. Nick responds to this and he says, first of all, there's been some questions about whether we can use ESRAM and main memory at the same time for the GPU, and to point out that really you could think of ESRAM and the DDR3 RAM as making up 8 total memory controllers. So there are 4 external memory controllers, which are 64-bit, which go to the DDR3, and then there are 4 internal memory controllers, which then are 256-bit, that go to ESRAM. These are all connected via a crossbar, and so in fact will be true that you can go directly simultaneously to DDR3 to ESRAM. And he continues by saying, over the LAN interface, each lane to ESRAM is 256-bit, making a total of 1024 bits, and that's in each direction. 1024 bits for write gives you a max of 109 gigabytes per second. By the way, in case you're wondering how he comes to that mathematical conclusion, you do 128 times whatever the clock frequency is, in this case, of course, 853. So anyway, we'll give you a max of 109 gigabytes per second, and then there's a separate read paths again running at peak of what would give you 109. What is the equivalent bandwidth of the ESRAM if you were doing the same kinds of accounting that you could do on external memory? With DDR3, you pretty much take the number of bits on the interface multiplied by the speed, and that's how you get 68 gigabytes per second. That equivalent of ESRAM would be at 218. However, just like main memory, it's rare to be able to achieve that for long periods of time. So typically, on external memory interface, you can be running up to 70 to 80% efficiency. The same discussion with ESRAM as well. 204 gigabytes is the number that was presented at a hot chip conference, and no limitation around the logic around the ESRAM into account. You can't sustain writes for absolutely every single cycle. The write is known as to insert a bubble, also known, by the way, as a dead cycle. Occasionally, 1 out of every 8 cycles is a dead cycle, also known as a bubble. So that's how you get the combined of 204 as the raw peak we can achieve over ESRAM. And if you want to say we can achieve it out in an application, we've measured at about 140 to 150 for ESRAM. That's real code running. That's not some diagnostic or some simulation case or something like that. That is real code that is running at that bandwidth you could achieve on external memory. You probably achieve a similar conditions up to 50 to 55 gigabytes per second. You add those together and you're getting an order of 200 gigabytes per second across the main memory and internally. One thing I'd like to point out is there are 4 8 megabyte memory lanes, but it's not a contiguous 8 megabyte chunk of memory within each of those lanes. Each lane, that 8 megabytes, is broken down into 8 modules that should address whether you can really read or write bandwidth in memory simultaneously. Yes, you can. There are actually a lot more individual blocks that comprise the whole ESRAM, so you could talk to those in parallel, and of course you're hitting the same area over and over again. You don't get to spread out your bandwidth, and that's one of the reasons why in real tests you get about 150 gigabytes per second rather than 204. That is not just 4 chunks of 8 megabytes, it's a lot more complicated than that. And depending how the memory, on how the pattern you get to use these simultaneously, that's what lets you do read and write simultaneously. You can get to add the read and write bandwidths as well as adding the read and write bandwidths to the main memory. It's just one of the misconceptions that we wanted to clean up. Andrew Goosen also added, I know it's a very long quote, but help me bear through it, guys. If you're only doing read, then you're capped at 109. If you're only doing write, you're capped at 109. To get over this, you need a mix of read and write, but that's when you're going back to look at things that are typically in ESRAM, such as render targets and your depth buffers, intrinsically have a lot of read and modified writes going on in the blends and depth buffer updates. Those are natural things to stick in ESRAM, natural things to take advantage of the concurrent read and writes. Now, I'm going to be honest, this is actually a lot to speak about, and I have addressed some of the ESRAM stuff before, but I'll go into it as an analysis towards the end, as a proper analysis. But there are a couple of things I do like Microsoft. I do like the fact that they're being honest about the realistic amount of memory bandwidth. Now, from my understanding, and from what developers have spoken about, it appears that the peak performance of the PlayStation 4's GDDR5 is actually higher. They are discussing about 97-ish%. They're basically saying it's around 170 gigabytes per second, thereabouts, within 1 to 2 gigabytes either way, really, which is pretty damn good, and it's better than DDR3. Now, there is a lot of different concerns that people have with ESRAM, and we're going to go into them more, but as the series progresses. But one of the big ones, of course, is it's just a very small amount of memory. We know, for example, that Microsoft expects you to handle texturing from DDR3. Now, 150 gigabytes per second, plus the fact that you can address DDR3 at the same time, fine, we'll go into that maybe a bit later, but let's just accept that just for now. But what they're basically saying is that when you're looking at things and you want to typically go to ESRAM, such as render targets and your depth buffers, intrinsically they have a lot of modified writes. Now, I know some of you may not be aware of what that means. Basically, what he's saying is that some operations, you're automatically going to have to adjust data. So when you're doing stuff like rendering, when you're accessing, say, depth buffers, which are, how deep a scene is, like basically making it 3D and stuff like that, you have to do updates. You have to constantly get a value, modify it, stick it back in. So in other words, that number is always going to change. And by a number, I'm talking about whatever mathematical equation or whatever the GPU is calculating. It always is changing. Therefore, in this respect, they are saying that most likely you're going to be, okay. So in other words, for the things that are mostly targeted towards ESRAM, as long as you're smart about it, you're going to be getting, 140 to 150 gigabytes per second constantly. I do like the fact that they're fairly honest with the number. Now let's talk about this argument that was really starting to pop up, because people were saying that Microsoft fudged a lot of stuff regarding the bandwidth of the ESRAM. One of the reasons behind this is they were stating that, well, you know what, how come suddenly, magically, that the ESRAM managed to jump from 109 or 100 whatever, because obviously back before the upclock of the GPU, how come they managed to basically double the speed? How could they have not figured this out? And so Nick responds, he starts out, when we started we wrote a spec. Before we'd really gotten into any implementation details, we had to give the developers something to plan around before we had the silicon, before it was even running on simulations, before tape out, and said that the minimum bandwidth was 102. Did it become 109 since they increased the GPU speeds? And in the end, once we got into implementing this, the logic turned out that you could go much higher. Andrew responded, Andrew Goosen, I just wanted to jump in from the software perspective. This controversy is rather surprising, especially considering the ESRAM is an evolution to EDRAM, which of course was utilized in the 360. No one questions on the 360 whether we can go to get the EDRAM bandwidth concurrent with the bandwidth coming out of the system RAM. In fact, the system design required it. We had to pull over all of our vertex buffers and all of our textures out of system memory concurrent with what's going on with the render targets. Color, depth, stencil buffers were in EDRAM. Of course, with the Xbox One, we're going to design it with where ESRAM has the same natural extension of what happened with EDRAM and the 360. To have both going on concurrently, it's a nice evolution of the 360 that you could clean up a lot of the limitations we have with the EDRAM. The 360 was the easiest console to platform to develop for. It wasn't that hard for developers to adapt to EDRAM, but there were a number of places where we said, gosh, the entire render target didn't have to live in the EDRAM. So we fixed that for the Xbox One. We have the ability to overflow from ES to DDR3. So the ES is fully integrated with our page tables, so you can have a mix of kind of mix and match between ESRAM and DDR3 as you go. Sometimes you want to get a GPU texture out of memory, and on the 360 that required a resolve pass, where you had to go into DDR to get the texture out, and that was another limitation removed from ESRAM, as you can now texture out of ESRAM if you want to. From my perspective, it's an evolution and improvement, a big improvement over the design we had in the 360. I'm kind of surprised about all this, frankly. I'm gonna quickly clear that up because he's not really making sense maybe to some people. What he's basically saying in regards to the resolve pass is that previously the ESRAM and the DDR RAM, you couldn't just say, you know what, we want to be able to load a texture, and I'm sure most of you know what a texture is, but it's basically just an image file. We can't just load that from the ESRAM. What you have to do, you have to copy that to the DDR memory of the Xbox 360, then you could use it. But now they're saying, well, you don't have to do this with the ESRAM. You could basically texture straight out of ESRAM if you want to. From what I'm reading in other interviews and so on, it's generally not considered good practice by Microsoft to do that because they consider it a waste of bandwidth, from what I understand. Now, the main problem with the ESRAM, and this has been something that I've been saying from the beginning, I don't like how much it was. I don't think that it was enough. I feel that Microsoft should have added more. Now, the problem with adding more is that you're going to basically make the chip bigger. And it's already pretty damn large, and they obviously had to reduce the GCN cores because of the ESRAM anyway. Now, I did mention previously that Intel had decided the EDRAM route and had utilized this with the Haswells and other GPUs because they basically thought to themselves, well, you know what, we want more. I mean, some of them have 32 megs, but a lot of them actually have 128. How they basically went with this is they decided, well, we're going to look at what we consider the minimum, and they went with 32 megs, and then they ended up basically doubling that, and then they decided to double it again. They doubled it once to 64 because they decided that's what most likely the future was going to hold, and then they decided to double it one more time just to be certain that there were no issues with games. It's worth noting that with testing for discrete GPU users for PC, they've actually found that the differences between, let's say, 1866 megahertz RAM wasn't actually that big a deal compared to 2133, and they actually found that latency was even less of a big deal. But you've got to remember that those GPUs are by no means as powerful as the ones inside the Xbox One. You've also got to remember that they've got a lot more EDRAM. They've got a lot more EDRAM in them. And so one of the concerns is that, you know, you could have multiple render targets. By the way, I realize that you may not be familiar with what a render target is and multiple render target. To clarify it, a render target is where the GPU will draw pixels that are being rendered by the title. And for example, you can get something like the back buffer, and that's where the GPU itself will have a part of the memory, and it will contain the next frame for the GPU to draw. So in other words, it's holding it for the GPU to actually create that frame of image. Because obviously there's multiple images that make up a game. In other words, for example, 60 frames per second equals 60 of these images. And it will have things such as how many bits allocated towards a pixel and how they're divided between, say, red, green, and blue and alpha. For example, for alpha channeling, and this is all for things such as color information and whatever else. But what can start happening is these can actually start ballooning up very quickly. And you can start getting situations where, a 1080p render target can quickly become pretty much half of the available ESRAM. And so, when you've got multiple render targets simultaneously, because that's what multiple render targets mean, you can see how that's going to start to eat up the memory. So the question is, can they do it so that some are in the DDR3 and some are in the ESRAM? And Andrew responds that you can indeed do so, and you can even make it so that portions of your render targets have a very little overdraw. For example, if you're doing a racing game and your sky has a little overdraw, you can stick those subsets or your resources into DDR to improve ESRAM utilization. On the GPU, we added compressed render targets format like our 6E4 and our 7E3 that were very, very, very popular on the Xbox 360, because instead of doing 16-bit floats per component, 64 pp, which render targets, you can do the equivalent using 32 bits. So that did a lot of focus on really maximizing efficiency and utilization of the ESRAM. And they can actually have the CPU read access the ESRAM, which, by the way, wasn't available in the Xbox 360. But the problem is, according to Nick, is that it's extremely slow. So here's the thing. I think it's cool. I think that, yes, you can be efficient. Yes, you can be careful with the memory. But I think there's still going to be issues with it. I mean, I'm still not exactly convinced by their choice of ESRAM, only 32 megs. I still think there's going to be issues. You're still going to be using DDR3 in times, and I'm not convinced really with... I mean, I think it's going to be better than what some people originally thought, but developers are currently saying it's a nightmare to work with compared to the PlayStation 4, and that's because they still have to be a bit more careful with the resources. I'm going to give more information on this though later on, because I want to get through some more of the interview because it's still pretty lengthy. And one of the things that we will clear up is that Microsoft never said that the GPU was anything to do with latency, so it's actually less latency sensitive, and they're saying they've not made any statements about latency. To be honest with you, from my searching around, it appears that the whole GDDR5 memory latency thing is a fabrication anyway. I mean, from my searching around, there's basically pretty much no difference between the latency of DDR3 versus the latency of GDDR5. The CAS may be higher, but it's being offset massively by the speed of the memory, by the megahertz, and therefore the actual latency, the real latency, is pretty much identical, with DDR3 being very slightly faster, very slightly. We're talking, 1-2 nanoseconds really, which is basically nothing. And CPUs and GPUs now have so much tolerance, it's not really that much of a big deal anyway. We're going to round things off by talking about the API, also known as DX. So obviously DirectX, I'm sure most of you are aware, have been around the block for a while now. It was originally used the DirectX was originally used to give the name for the original Xbox, and of course variants of the DirectX have been, of course, in the Xbox, the original Xbox, the Xbox 360, and of course now the Xbox One. So the question was, how do you actually utilize this API, because the API is very mature. So the problem is you get a lot of redundant instructions unless you do something about it. So Andrew said, and I quote, "To a large extent we inherited a lot of the DX11 design. When we went with AMD, that was the baseline requirement. Then when we started off the project, AMD already had a very nice DX11 design. The API on top, yeah, I think we'll see a big benefit. We've been doing a lot of work to remove a lot of the overhead in terms of implementation, and for a console, we can go and make up what you call a D3D API, that's Direct 3D API. It writes directly to the command buffer to update the GPU registers right there in the API, that's Application Programming Interface function, without making any function calls. There's not a lot of layers and not a lot of layers of software. We did a lot of work in that respect. We also took the opportunity to go and highly customize the command process on the GPU. Again, concentrating on CPU performance, the command processor block interface is very much a key component in making the CPU overhead of the graphics quite efficient. We know the AMD architecture pretty well. We had AMD graphics in the 360, and there were a number of features we used there. We had a feature like pre-compiled command buffers where developers would go in and pre-build a lot of their states at the object level, which would simply say run this. We implemented it on the 360, and it had a whole load of ideas to make it more efficient and a cleaner API. So we took that opportunity with the Xbox One, and with a customized command processor, we've created extensions on top of the D3D, which fit nicely into the D3D model, also known once again as Direct 3D. And this is something we'd like to integrate into our mainline 3D on the PC too. This small, very low level, very efficient, object-oriented submission of your draw and state commands. Now I realize a lot of that might not make sense to people, so I'm going to go ahead and clear stuff up. One of the problems with DirectX, and you can learn a lot more about this, by the way, if you watch my Mantle videos. So you can just search Mantle, that's M-A-N-T-L-E, of course, and you can search for that. But Mantle is a great example of low-level optimization versus high. The problem with DirectX is that on the PC, and before Microsoft had made a lot of the changes for the Xbox One, that there's a lot of overhead. For example, draw calls take a lot of CPU resources to issue. So what happens effectively is, let's just make a number up, and let's just say that you need to do 10 draw calls, right? So you want to issue 10 draw calls. Well, what can happen is your GPU might be able to handle all of those, but your CPU might start slowing down a bit if you go above 8. And this is obviously just making up figures just to give you an idea. So what happens is that when you start getting low-level access, you can get many times more draw calls because you're basically not using so much of a software layer previously to add extra computation into the CPU. In other words, the CPU is doing a lot less work, there's a lot less middleware. Think of it as a lot less red tape. That's the easy way to think of it. And so what Microsoft is saying is that when they're doing this, they are removing a lot of the overhead, because it's a static application, right? So there's not, the video card in there, there's not multiple AMD cards that could possibly be in there. It's not like they could be using multiple memory setups or whatever. It's all fixed. So what they can do is they can actually utilize that hardware to best get the performance possible out of the machine. And that has multiple improvements. Like, one of them is that they can reduce the overhead for the CPU. They can reduce the amount of latency for it, and they can get much more work out of the GPU, and they don't need so much of a powerful CPU. And Microsoft, as we're going to speak about in a minute, have said multiple times that the CPU is actually the area that they had problems with in terms of performance. It's actually not been the GPU. In other words, they found that the CPU, especially when they overclocked it or upclocked it, not overclocked it, when they upclocked it, they found that they actually got much more performance out of that than what they did even with increasing the amount of GPU power. So they're actually saying that they were somewhat CPU bound. So a lot of this stuff that they're talking about is basically to try and reduce the overhead of the GPU. For the CPU to reduce the overhead. They're trying to improve the architecture so that they've got libraries there which allow much better simple and pre-baked commands, so the developers can simply issue those commands very easily into the hardware. They don't need to worry too much about how that's implemented. The commands and the features are already pre-compiled, which is pretty important because that means they're basically ready to go. For example, what compiled means is the program has already used its executable or DLL or whatever that's compiled, versus source, which is, it's pretty much just code at that point. And there you go. So they're basically saying that a lot of this stuff, they've improved it, they've allowed you to not need to, for example, go through various function calls. They've allowed you to be able to write directly to a register without needing to, go through multiple layers of software first, or be able to basically have to go to one side of the world to the other. Equivalent of, let's say you're in the United States and you want to come to the UK, it's basically they're saying, well, they've improved it a lot now, so rather than having to fly to, say, Germany, and then to France, and then to the UK, you can now just hop straight onto a plane and you can get straight to the UK. So hopefully that's cleared it up. They're just making it a lot simpler, a lot less overhead, which is all very important stuff, and drastically, of course, improves the performance of a console. Anyway, this has come to about 32 minutes long, and I still have stuff to do, unfortunately, so we're going to continue this later on. Hopefully you're enjoying the series. I'm going to have maybe 1 to 2 more of these up tomorrow. I'm trying to cane through it because I've got so much other stuff that I need to do. I still need to speak about the PlayStation Shade language. I'm beginning today a post-mortem of the PlayStation 3. I need to do the same for the Xbox 360. I'm going to be doing some programming stuff as well for the channel, and we're going to, of course, try to do a lot more PC stuff, and, well, there's dozens of different projects that I'm trying to work on. So anyway, hopefully you've enjoyed the video. I'll see you soon. Take care. Bye for now.